Okay, in this video we're just going to take a look at some more rules. Actually, we're going to be looking at notation for the derivative and then some applications. So notation for the derivative. So our initial notation is, if f of x is a function, be a function, right? We used f prime of x to denote the derivative. But sometimes we're not sure what variable is being used as the independent variable and which variable is being used as the dependent variable. And so in that case, it's nice to have different notation that tells you that. And so alternative notation is something like dy over dx, where this is saying that y is our dependent variable and x is the independent variable. Okay, so we're thinking of y as our function, or y is our variable for the function, and then x is the independent variable. Okay, so this has the added advantage that you can actually use that fraction as an operator. So here, this is short for differentiate with respect to the variable x. And then inside some parentheses would be our f of x. And so to differentiate, we just compute the derivative. Okay, so that's kind of handy notation. For the second derivative, we would say d squared dx squared of f. So that would be our second derivative. And of course, to take the second derivative, we just take the derivative of the derivative. Good. And then, of course, you could also use parentheses with the prime notation. I think those are the only ones we're going to use for right now. There's some other notation as well, but we'll stick with those. Good. So let's do some quote-unquote applications of the derivative. So suppose that p of t is equal to 2t plus 3 to the t, and we want to find the equation of the tangent line. At let's say t equals 0. Okay, so the point that the line goes through then would be 0 f of, or 0 p of 0, right, which in this case would be 0, and then 2 times 0 plus 3 to the 0 would be 1. Okay, and then the slope would be p prime of t, which in this case would be 2 plus 3 to the t times the natural log of 3. Right, so at p prime of 0, it would be 2 plus 3 to the 0 is 1, so 2 plus natural log of 3. Okay, so that's our slope. And now we could just write our equation in point slope form. 0 minus 1 is equal to 2 plus the natural log of 3 times x. Well, x minus 0 if you like. Good. All right. Similarly, if we were saying, a function for like temperature control might be something like 95 times 3 to the, let's say 1/3 to the t, 1/3 to the t plus, if I can get that to work, plus 5. Okay, so that's a function for temperature at time t. So what is f of 0 going to be? Looks like 95 times 1/3 to the 0 would be a 1 plus 5. 5, so that would be 100. Okay, and then what would f prime of 0 be? So that would be a constant times our 1/3 to the t times our natural log of 1/3, right? And then plus 0, right? Because the derivative of the 5 there is 0. Good, and so then that's our general formula. Then we would want to plug in t equals 0 to get 95 times the natural log of 1/3. Good. All right. Let's try another one. How about like a table of values? So here's my, let's see, f prime. No, that's not how I want to do this. Sorry about that. Let's say f of 2 is 5. F prime of 2 is 3. G of 2 is equal to 1, and G prime of 2 is negative 1/2. Now, what would, if our, let's say our capital F of t is equal to 3 times f of t plus 2 times g of t, then let's compute f prime at 2. Let's see, so what would that be? F prime of 2 would be 3 times little f prime of 2 plus 2 times little g prime of 2. Okay, so those values are already listed there, so that's 3 times, let's see, f prime of 2 is 3 plus 2 times our g prime of 2 is minus 1/2. Good. So therefore we have 9 minus 1 equals 8. Good. All right, we'll stop there. This has been looking at some notation for the derivative and doing some applications.